everyone, and welcome to the scientific method. Now, there's always been one question that's always been boggling my mind, and it's that whether you're on Saturn, Jupiter, Venus, or even our home planet, Earth, there's one thing common between all of these celestial beauties, and it's that all of them are round. Yes, it's not that complicated to figure out. Anybody who's attended a science class in their school knows that all planets are spherical. Except for flat earthers. But the real discovery lies in the why. Why is everything in space round? Why is it not triangular or square shaped? Well, in order for us to answer this question, we will first have to understand the force that keeps us on the ground and keeps all the planets together in our grand solar system. This force is gravity. From falling apples to cosmic unification, gravity just keeps on leaving us humans in awe, especially me, because its remarkable features and its constant presence in nature just keeps on popping up everywhere we look. It's just like those ads that pop up on YouTube that just keep on reminding us that nothing in life is ever free. Thanks to our good friend Isaac Newton, we know a lot about gravity. Like a lot, a lot. Like, I mean the ability to go to space a lot. And as most of you must know, gravity is a force that attracts objects to one another, towards one another. For example, if I have an object A and I have an object B, gravity would be the force that brings these two objects towards one another. And the more mass you have, that being the more of an object that you do have, the more gravity you have. Simple, right? Picture you have a book in your palm, and then zoom into it 1,000,000,000,000,000 times, as far as you can go. And once you zoom into it into such excruciating detail, you see these tiny little jiggling balls moving all about with such oomph and such energy, and they're moving, vibrating, jiggling about in the same position. These tiny little jiggling balls are called atoms, and they exist in all things: your laptop, human beings, living things, a tissue box, a book. Everything that exists contains atoms. In all objects, for example, this book, there exists a point called the center of mass. And what the center of mass is, it is a point on the object, for example, again, this book, in which all of the mass seems to be concentrated. For example, this book has 146 pages. Since this book's mass is evenly distributed, that meaning that not one side of the book, left or right, top or bottom, is heavier than the other, that means that the center of mass of this book is in the exact middle. But since this book is three-dimensional, that middle would be inside the book. So it would be at 146 divided by 2. At that page would exist the center of mass, and that is page 73. So the center of mass is exactly here. However, for other objects, the center of mass is not exactly in the center. Like earlier we talked about the book, the book being in the middle. And even with the ruler, it's the same. If you have a 100-centimeter ruler, and since a ruler, its weight is evenly distributed on each side, that meaning one side is not heavier than the other, that means if you have a 100-centimeter ruler, that means at 50 centimeters, that is the center of mass. That is the point where all of the object's mass is concentrated. However, you can have an object such as a hammer. With a hammer, at the hammer end where you hit the nail onto the wood, for example, it is much more heavier than the base part where you hold the hammer. That metallic bit is much more heavier. So that means that if the hammer is 50 centimeters, and if you're measuring it from the place where you hold it, that means the center of mass should be at about 40 centimeters, because that's where most of the mass seems to be. Back to the book though, its center of mass is going to be at page 73, as we mentioned earlier, because its mass is evenly distributed, one side being not heavier than the other. So, this means that all the atoms inside this book, all of those little jiggling balls that we mentioned earlier, are going to be pointing towards that center with the same force. They're going to be attracted to that center all around with that same force because of the gravity. So, it's going to be really abstract now, because I want you to imagine a book the size of the Earth. Yes, a book the size of the Earth. I'm talking about masses of million kilograms. So bear with me, I need you to imagine a book the size of the Earth. So now what happens is that we said earlier that more force, more mass equals to more force of gravity. That means that the more mass you have of an object, the more force of gravity you have. So that means that all of those atoms now are pushing towards the center. They're getting attracted towards the center with such an immense force. I want you to picture that. Such an immense force. They're getting pushed, getting squashed together. Imagine millions of people trying to fit into such a small room. That's exactly what you should be imagining. And all of them are just shrugging in. So what happens is that if all of those people are trying to squash into that center of that point, yeah, all of them are trying to get into the center. Not all of them are going to reach the center. So what's going to happen now? The person at the closest will end up being at the center, right? But then now think of it going outward. All of those people will be stacking all around, stacking side by side. There'll be people still trying to push in, but they can't push in because it's impossible. That's exactly what's happening in the book. All of those atoms are squashing, trying to get towards the center because they're getting pulled towards the center. So this causes those stacked atoms all around the object. It causes a uniformity, a uniform circle, because all around this pattern is getting duplicated. Atoms are getting stacked on top of each other. To the left there's an atom squeezing, to the right there's an atom squeezing. So all of them, with this immense force, all of these atoms inside the book will end up forming the structure of a circle, because with this amount of force pushing towards the center of the object, the book in this example, you're going to get a circle, because all of these atoms are pointing towards the center. And with all of these atoms around pointing towards the center and getting pushed towards the center, you get a circle. I want you to just picture what I just said. The whole structure of this book has been deformed and changed just because of a center. Because all of those little individually, those atoms make no difference. But in the grand scheme of an object, because there's such millions of them, the whole structure of the object has been deformed because of an increase in the force, because we had just a larger object. I know the scale was massive, but then the whole structure of that object has been changed, and changed into something such as a circle, just because the mass has been increased. And it's not like it was deformed into clay or a shoe or something irregular. It's been structured into such a perfect circle. Nature's so structured, right? To visualize this a bit better, you do not need to be an astronaut on the International Space Station or even use this scary looking formula. All you need, and I need you guys to believe me on this, just trust me here, okay? All you need is a tape measure.
Nice.
I am not joking. The answer to why everything in the heavens is round, lies in the tape measure. I am not crazy. This is serious. I'm not crazy. So, find the nearest tape measure you have, extend it as such, and you will see that it forms a bend. Now, if you keep extending it further and further, you will see that the tape measurer just collapses. Well, the reason to why the tape measurer collapses is not because if you have an Earth-sized book, for example, it will just deform into a circle. Actually, the reason to why the tape measurer collapses is because the force of gravity is acting downwards at the end of the tape measurer. So, why on earth am I showing you a tape measurer? See what I did there? Why
No,
on earth?
God!
Because we're talking about
No, God,
planets
please,
and
no,
circles
no!
and... Well, the reason to why I'm showing you this tape measure in the first place is because it so nicely visually shows us why straight-lined objects cannot exist in space. It collapsing towards the center perfectly matches up with our description because if we have an Earth-sized tape measurer, for example, all the atoms pointing towards the center and with such a large immense form, it would deform the tape measurer into a circle, and that is exactly what is shown here. And since we do not have enough funding to get a Earth-sized book or even an Earth-sized tape measurer for that matter, which I could get if I was sponsored, my dad's old tape measure will just have to do for now. What? Oh my god. Thought I put my phone on silent. What? I'm so sorry, guys. I have to take this. Just give me a second. Hello? Yeah, this is Hilim. Yeah, I know this is the University of Princeton's physics department calling. Yeah, I saved your number from the last call because Professor Eisenman couldn't find his phone. The professor wants to talk? Yeah, of course. Just connect me to him, please. Good afternoon, Professor. How are you? Tell me, Professor, what's up? I'm good too. I'm good too. By the way, I forgot to tell you, I finally got to finishing you and Simon Warzow's book on the disorder effects on quantum systems. Sorry, quantum spectra and dynamics, yes. Which did involve some quantum systems, yeah. But to be honest with you, Prof, I didn't get most of the math because my math level is not that high. Yeah. Mathematically, I could not understand your Anderson model. But I did kind of get the general gist. Don't get me wrong, Professor. So wait, you didn't call me to talk about quantum systems, sir? Then, with all due respect, why did you call me? I'm wrong? Sorry, sir, but what am I wrong about? Gravity is not a force? What do you mean gravity is not a force? Newton is wrong? So you're telling me all this time Newton is wrong? What do you mean Newton is wrong? Sorry, sir, but I do not understand what you mean by Newton is partially wrong. Okay, then go ahead and tell me who's right. Einstein? So in which one of Einstein's papers does he prove relativity? His general theory of relativity. Well, what does it say? It's a long story? Sir, you went ahead and called me on a Sunday. You might as well just tell me this long story. Okay, how about this, sir? How about I call you in about an hour? And but I'm still recording and I need to finish up my recording. How about I call you in an hour? Skype? You want me to call you on Skype? Sir, my Skype account has not been active for about 3 years now. So nobody uses Skype any. Okay, I'll call you on Skype. Fine, sir. Yes. Bye. So I guess gravity is not a force. But then if gravity is not a force, what is it?